Morning, everybody.
Morning.
I give myself a good, solid 95%. Remembering your names. And ask a couple of you, which is pretty good. Keep working at it. We have, let's see, chapter. We gotta talk about that. Chapter 2 homework is due this Saturday. Chapter 1 part 2 is due this Saturday. And then chapter 3 homework, we're starting chapter 3 today. Chapter 3 homework is due next Wednesday. And why is chapter 3 homework due next Wednesday?
That's next Thursday.
Yeah, there's a test next Thursday, right? So we have today and Tuesday to cover chapter 3, which is doable. And then, no, that's not true. I have today to do chapter 3. Because Tuesday, what are we doing? We're reviewing for the exam, right? Now, there is a issue that I need you to think about. We're not going to vote on it today. I was informed and taught and told by you and several others, thank you very much. The tutorial center is closed on Saturdays now, but open on Sundays. And I often want to give like a day after grasp, right, for you to have a weekend to finish things up. So the homework being due on Saturday, there's no, you can't go to the tutorial center to get help kind of thing. So I'm thinking about moving the due date for homeworks, right? And I feel like we can move it two directions. We could move it from a Saturday to a Friday, which I know causes fear and trembling and all that kind of stuff in you. Or we could move it to like a Sunday, right? Because the tutorial center will be open that day if you need some extra help, that kind of thing. And honestly, I'm kind of split as to what to do, right? Moving it to a Sunday, like on test weeks, you'd have homework due on Sunday and then another homework due on Wednesday, right? Okay, it sort of compresses things even more. So I'm uncertain what to do. I would give me feedback, shoot me an email or something like that, canvas message, right? If you feel strongly one way or another, oh my gosh, Mr. Balogh, it would end my life if you made it due on Fridays, or it would be great if it was due on Sundays, or my life would be over, or don't change anything. Like if you have a strong opinion one way or the other, please, please, please let your voice be heard, let me know. Maybe we'll make adjustments for the second unit. Right, or maybe if the homework system, the way it's working right now, is good for you, fine. Right, let me know that too. But I'm listening your feedback here because I honestly don't know what's best for you in terms of your life situation. Like I know it's best for you in terms of like learning and keeping the schedule and all that kind of stuff. But sometimes the theory of what's good for you doesn't hit the practical of what's good for you. So let me know. And I'll take everything into consideration. And we will maintain the illusion of democracy. Okay. So there was that, and then, okay, so chapter 3. Chapter 3, the bad news is that chapter 3 is a big chapter. The good news is that chapter 3 is pretty much what you've already done in chapters 1 and 2. So we're basically bringing everything together for chapter 3. And we're doing it in this thing called projectile motion. Okay? So, strictly speaking, again, these definitions of these terms have very specific meanings, and you got to grapple with learning those along with everything else, right? A projectile is any object that is in free fall. So like free fall we know is gravity only, right? But up to this point, we've made sure that when we're doing free fall, we're only either just dropping something straight down, or we're throwing it straight up and down and it comes back, right, in just a line. A projectile is anything that can move as long as it's in free fall, right? So as soon as I toss this ball, it's in free fall. Do I have? Oh, I do. I forgot to practice. Let's see if I can do it. No practice. It's been a whole semester since I tried. Okay. Oh, there we go. Okay. So it's like riding a bike. You fall a lot. So what is true about each ball after it's left my hand? It's in free fall, right? Is it in free fall on the way up? Yes. Is it in free fall on the way down? Yes, because remember, free fall is all about gravity only. And yes, I can juggle and lecture at the same time, right? So I can do it, you can do it. Not the juggling part. Well, the juggling part, yes, but you're just juggling life, right? Your balls are your classes, right? Which one's going up, which one's coming down at what time. But all of those are in free fall, even on the way up, even on the way down, because gravity doesn't turn off. But what we're going to do now is we're going to combine a motion, right? Which is strictly a vertically up and down motion where gravity only acts up and down, with a sideways motion, right? Only we'll be very careful about the accelerations. Projectile motion means that the acceleration in the y direction is going to be that acceleration that gravity imparts to all objects. It also means that we are going to set the acceleration in the x direction to be 0. So we're not going to change the motion horizontally speaking, okay? All we're going to do is change the motion in the vertical. So what does that do to our toolbox? Well, remember our toolbox, so we can write down 2 toolboxes, 1 toolbox, 6 equations. It's really only 3 equations. I can write the tools with the coat of paint where everything is in X. I think I did that one right. I often screw these up, so 2A delta. Okay, so there's the toolbox where everything's written, just, it'd be like horizontal, right? This is a chapter 2 problem. Car speeds up, something slows down, whatever, right? Okay. And then I can write it down. Same tool. Again, different coat of paint. What's the difference here? It's just in the y direction. Okay. The y, okay. This is where copy and paste would have been really useful. Okay, right? So there's the y direction. But if we apply these rules of projectile motion here, okay, what happens to every term that has an ax in it? It's 0, isn't it? And this is supposed to be an ax. So right, so like this term goes to 0, that term goes to 0, that term goes to 0. And if we take a look, like, let's look at this right here. What is that saying? We're not changing the velocity beginning to end, right? Horizontally speaking, this thing isn't going to speed up and it's not going to slow down. Whatever we start with is what we end with in the horizontal portion of the motion. Third one does the same thing, only worse, because it's got squares, right? Okay, you got a square root. But essentially, the first and the third equations become useless in the x direction. They're not going to really help us at all. They're telling us something we already know, but it's not very useful. So that means it must just be math, right? Low blow to all the math teachers. Okay, so what survives? This statement right here. Distance equals velocity times time, which I know you already knew. And then all the y1s survive because nothing goes to 0 in there. And so our toolbox for chapter 3, right, where something is a projectile, it's launched through the air, okay, consists of the 3 equations we know and love only in the y direction, and then this horizontal, dare I use the word, component. Uh-oh. Where have you heard the word component before? Yeah. Right? Okay? So we need to incorporate vectors into this. And to show you how this works, let's just jump into an example problem right away. Okay? We'll just jump into an example problem right away, and we will see what happens. And my hope, by the time we're done with this, is that this looks familiar. Like you're like, oh, okay, I've done something very similar before, right? Now what I want to do is I want to replicate the toolbox up here. I'll put it over here. Where did I put it last time? Did I put it here or here? Shoot, we'll put it right here. Let's see. So the toolbox is Vy equals V naught Y plus AYT. I want this up here to be able to reference it. I know, I could copy paste on my iPad, but I'm not good at that. Vy squared equals V naught Y squared plus 2AY. Do you have to have these memorized? No, why not? You get a cheat sheet, you get a summary sheet, all that kind of stuff. Right? I don't require, memorizing equations isn't going to get you anywhere, okay? Do you have these memorized yet? Like it's almost there, isn't it? Right? You use them so often that they tend to start sticking. But I wouldn't trust that. I would make sure that you get these down on your cheat sheet. Remember that sheet you get to bring with you to the exam, right? Make sure you have a correct version of these down. Because I won't give them to you. Come up to me and ask me, hey, Mr. Bailey, what's the second one? I'll be like, Okay, so they are important. All right, so you can see here that the toolbox, okay, is just slightly modified. It contains just one extra equation in it, which is our horizontal component of our motion. Okay, so I need an object. This is where you guys get to decide what it is we're going to launch. What's something that you want to see launched off of a cliff into the, is it the ocean below? Doesn't say. Okay. Yes.
One of those white plastic chairs.
Oh, like a garden chair?
Yeah, like the ones you see everywhere.
Oh, okay, but that would introduce plastic into the environment. We don't want to.
You can see the picture of one at the bottom of the ocean.
Right. Yeah, we don't want more plastic in the ocean.
About like a big rock.
A big rock?
Maybe one of those that made out of like paper mache.
I love it. I love it. Your creativity is great. Rock's a little bit, normal. Come on, let's think way outside the box here. Come on.
Compressed tungsten.
A tungsten cube. Tungsten is one of the densest materials that you can find on the periodic table. Okay? So let's hung some tungsten. Right? We're gonna yeet some tungsten off the cliff. All right. So, tungsten cube. No, come back here. Okay. Imagine like something about the size of a bowling ball, but weighs like 10 times as much. All right. What do we got here? We've got a cliff. So first step, right? Okay, so the first step when encountering any physics problem is panic, right? Absolute sheer panic and terror. And one of the goals in this class is teaching you how to not run away screaming in fear, run home, jump in bed, pull the covers, assume the fetal position, pull the covers up over your head and try to ignore the rest of the universe, okay? So once you get over that, right, first step is what? Visualize. Right? We've got to get some stuff down. This could be a picture, it can be a list, it can be both, right? Do something to get the picture in your head. So I'm going to draw like a cliff, okay? And it doesn't say what's at the base of the cliff. We'll pretend it's a lake or the ocean or something like that, okay? And then we have this tungsten cube, right? And it does say that we launch it at a 50-degree angle. So I'm going to draw a vector that represents the velocity that this thing leaves at. And I've been given a velocity, haven't I? How do I know it's a velocity? It's got speed and direction, an angle associated with it, right? That's the key, right? Speed isn't velocity. Velocity is speed with direction. So those terms are not interchangeable. And I know you've grown up thinking that they are. Again, that's one of those pieces of knowledge that needs to be replaced. So I've got this, it's 40 meters per second at an angle of 50 degrees. So that's how I'm gonna draw it right there, okay? So Does this toolbox speak 50 degrees? No. What does it speak? These first three equations are strictly what direction? Y, the vertical direction, right? Okay. And this fourth equation speaks which direction? Only x. So key thing in chapter 3 that you need to do is break up any velocity they give you into its component parts. And this is why we studied vectors. How do I get that vector into just x and just y pieces? Trig, right? We got to do the trigonometry. And so maybe it's just easier for you if you come over here, maybe down below, and you go, okay, I've got a vector, right? And it's 40 units long at an angle of 50 degrees. And now if I come along and I want to get the x component down here, the part that points along the x-axis, sine or cosine? Cosine. Why? You're able to do that so quick, right? It's ridiculous. So it's going to be 40 cosine 50 degrees. And what does that leave for the y component then? Sine. Well, you already used cosine, right? So that's a clue. But it's also not touching. 40 sine 50 degrees. So we're going to find what that is, right? Let's see. Other visualizations that we've got here. They gave me a number. They gave me the cliff is 75 meters tall, right? Okay. And that seems like it's all the numbers they gave me, isn't it? It doesn't seem like very many numbers. Are there any implied ones? Is there anything that suggests that this thing has zero velocity? Doesn't say it comes to a stop or anything like that, right? Will it come to a stop once it hits the water? Yeah, but is that projectile motion? It's no longer gravity once it hits the water, right? Okay, so we can only analyze from the time it's launched after it leaves the launcher, hand, whatever's throwing this thing, right? To wind right before it hits the water. Okay, so this, you can come in here maybe and draw like a little path that it does, okay? Don't get too excited about the drawing, focus on the physics. So let's make a list, right? Let's see, what could be in my list? Vy, V naught y, Ay, delta y, oh I forgot the t, Ay, t, delta y. So those were the sort of standard things that we had from before. And again, I just read those, right? I just started here and went through, okay? And I picked up new stuff as I went along until we get to this one. And now I can add a delta x and a v naught x, right? So just a couple more things to get added to my list. But I'm going through the same problem solving method. Details are slightly different. But hopefully, again, this looks a little bit familiar. So, we go down this list. What do we know? What do we not know? Do we know anything about how fast this object is going when it hits the water? Vy. What is Vy?
The velocity in the y direction.
The vertical, the final vertical velocity. Do we know anything about how fast it's going vertically when it hits the water? No. We don't know anything. Does it tell us anything? No. Can we assume it's zero? No. Where is the only place Vy is zero? At max height. It's the only place that the vertical speed can be zero. Because everywhere else is going to be positive or negative. Okay? So when it hits the water down here, it will have a vertical component. It'll have a horizontal component, but I don't know what those things are. So I don't know what Vy is, so we'll put a question mark on there. Do we know the initial speed in the vertical direction? Do we know how fast it was going at launch vertically? Yeah, it's 40 sine 50 degrees. We found the component, right? So this is going to be 40 sine 50. I didn't do that. It's 30.6, and it's positive 30.6. Why is it positive? It would launched upwards, right? Okay. Do we know the acceleration in the y direction? What is it? It's negative 9.8. Why is the negative sign there? It's going down. Okay. Do we know anything about how long this thing was in the air? No. Okay. Do we know the vertical displacement? Not 75.
I'm confused on
Yes.
the AY.
Okay.
When does it go down? Are we doing this when it's launched up or when it's going back to the water?
Okay. Right? This is, Kamari's asked a very, very important question I know is in the minds of 20 more of you. Okay? Why is the acceleration negative everywhere? Because the acceleration comes from gravity. Acceleration is not motion. On the ball, when the tungsten cube is on the way up, what direction is its velocity? Positive. And when it's on the way down? Negative. But what direction does the acceleration point the entire time? Always in the negative direction. In other words, gravity doesn't change its direction, right? Yeah. Gravity only points down. Yeah, and you want to do that a lot. I know, like, you just want to, like, no, but the acceleration's up on the way up and it's down on the way. You're talking about velocity. And again, very easy to confuse those terms. One.
Could acceleration be more than 9.8 if you're like throwing something downwards?
Okay, wonderful question, right? Instead of yeeting this cube up like this, what if we just threw it straight downwards? As soon as it leaves my hand, what's its acceleration? 9.8, downwards, negative 9. Why? Because only gravity is acting on it after that, right? While it's in my hand, it's whatever it is. We haven't talked about that yet. It's coming up in the next unit, okay? But we are simply talking about when this object is a projectile. And it's only a projectile if it's in free fall. And it can only be in free fall when? Only gravity is acting on it. And as soon as only gravity is acting on it, we know the acceleration is 9.8. Doesn't matter what size it was. Doesn't matter how fast it was going in the beginning, any of that stuff. If we did throw it down, we'd have to put a negative sign on the initial velocity. You guys are thinking about it. That's fantastic. It's wonderful, right? That you're thinking about these things. Okay, the delta y is not 75. Why is it not 75? Because it's negative 75. And again, that negative sign is going to burn you. Why am I putting a negative sign on that 75? It goes down. Now, like some of you are saying, but Mr. Balogh, it goes up first. Yes, I know. But delta y is a displacement, right? It's a comparison about where something started versus where it ends up. It doesn't care about what happens in between. So with delta y, if the object ends up lower than where it started, its displacement has to be negative. Okay? So what happens if it ends up higher than where it started? Be positive. Right? Displacement isn't distance. Okay. Do we know how far horizontally from the launch site this thing went? No. Okay. Kamari, go ahead.
Why is it negative only 75 if it was launched up?
Okay, it's displayed. Okay, so remember how this was 0, right? Okay, so if I go 1 meter this way and then 2 meters this way, what's my displacement, positive or negative? It's negative. I ended up to the left-hand side of my 0 point. This object ends up below where it started. So it moved in the negative direction. And that's what delta y is capturing. Which way did this thing move? Where did it end up? If it ends up below where it starts, negative. If it ends up above where it starts, positive. And what happens if it ends up at the same elevation where it started? Then it's 0.
But it went up, it got launched up.
Yeah. The toolbox knows that. It takes care of that for you. Yeah. It's magic. Science. It's physics. The one thing to kind of clear up here though, right? If you tell the kinematic equations that Vy is equal to 0, what have you just told these tools to figure out? Like, what have you limited them to? Max height, right? When you put a final y or an initial y of 0, right? Any of these vertical velocity 0, you've told it to either end at or start at the max height. In which case, the delta y it's going to give you will be the displacement to maximum height, right? So you do have to be careful about what you feed the tools. The tools don't think for themselves, right? But they are able, as Kamari is pointing out to us, they are able to handle the fact that yes, this object goes up and then comes back down, but that's okay. As long as we capture acceleration in the correct direction, displacement in the correct direction, and initial velocities in the correct direction, the toolbox can handle it. All right, do we know anything about how fast this thing's going horizontally when it starts?
Yes.
Yes. It's 40 cosine 50 degrees, which is 25.7 meters per second. Is it safe to say that this seems to be one of the most difficult parts? How often are you making mistakes on these signs? Like all the time, right? Okay. This I think is the hard part of the class. After this, you're like getting to the point now where you're like begging, can I just do math now, Mr. Balogh? Stop making me think. Hey, dude.
Is that positive or negative 25.7?
Oh, good job. Good man. Reminding me to put my signs on there, right? Okay. So, what do we, I don't even know what we want. What do we want? Find A, the maximum height above the ground at the base of the cliff. Oh, okay. Well, I haven't set that up. Let's do B first then. Let's do total time of flight. Because that's kind of what I've set up here, right? Okay. So, total time of flight. What equation could I, okay. We want T, right? So if we're doing part B here, we want T. What do we not want to have in our equations? We don't want a Vy. I got a question mark on a Vy. I'm not being asked to find it yet. I want something that's got V naught y, A y, T, and delta y in it. That's the second equation, isn't it? So what's the plan? Use second, right? So the second equation, delta y, V naught y, T, plus 1/2 A y, T squared. We're going to use that equation to solve it for T, which means what? Quadratic, doesn't it? Means quadratic. Is there another way that I could avoid using the quadratic? Use the third and then the first? Yeah, okay. Or, choose your own adventure, use third, solve for final y velocity, then first solve for t. That word is supposed to be solved. That word didn't end up being solved, did it? Solve for t. Alright, so which one do you want to do? You want to do quadratic? Or do you want to do first and third? Third and first. Quadratic? Quadratic? Third and first? Oh, okay. Alright, let's do fight. Fight! Let's do both. Why would we do both? Check, right? We can check ourselves using both. And they're going to ask me for the components of velocity to impact anyway. Looking ahead, right? Part D. So, okay, all right, I'm up, okay. So doing the quadratic, setting this up, okay? This is gonna be negative 75 equals V naught y, which was 30.6 t minus 4.9 t squared. You've got to rearrange that. I've had several questions about this. This needs to be in the form of ax squared plus bx plus c equals 0, right? So I usually do that by moving stuff around. Minus 30.6t minus 75 equals 0. I took the entire right-hand side, I moved it to the left-hand side. And when you do that, what happens to the signs on things? What? It changes, doesn't it? Right? So what was positive becomes negative, what was negative becomes positive. Aiden?
Shouldn't we be attaching meters onto the 75?
I don't put units in here because I've got standard units in here, right? So I'm not worried about my units now because dimensional consistency. So this is A, this is B, and this is C, right? So I throw those into my quadratic equation and I get negative 1.88 and 8.12. I get two answers. All right. One's negative, one's positive. You'll just have to trust me on this next bit. But we could set this problem up so that you get exactly the opposite answer. You get positive 1.88 and negative 8.12. It's actually not hard to do it that way, okay? So in the end, it turns out that depending on how you set up the problem, you can end up with a switching of signs on these answers. Which is why just picking the positive answer doesn't always work. Now, I'm not going to go out of my way to trick you about this or anything. I just want you to take one step further and think about why two answers were given to you. We asked this math, at what time is this object 75 meters below where it starts? Mathematically, the math has no way to know what's real and what's not. What it does know is that the path of this projectile is a parabola. We're solving a quadratic equation which gives us a parabola, right? We're starting up here, 75 units in the vertical direction, and we said, okay, where or when, what time, right, is this thing 75 meters below this point? And so it answered for us. It said one of those points was at negative 1.88 and the other point was at positive 8.12. Which of these answers is the real physical answer and how do you know? Why is it the positive one? Not because time can't be negative. The path of the object takes up the bigger portion of this parabola, doesn't it? This object has to go up and then come back down again. And the 8.12 represents the entire time it takes to do that. What does the 1.88 represent? The smaller part of this parabola. This parabola was divided into two parts, a longer part and a shorter part. Which of these two is the physical part? The longer part. So even if I had gotten positive 1.88 and negative 8.12, I would have known that I needed the bigger value, the magnitude bigger value, because I've got more of the path of the parabola to get through. If we had launched it down like this, okay, the parabola, the mathematical parabola would have looked like that. And then what part would we have taken? The smaller part, right? Because this other part doesn't physically exist. Okay? So math can lead you astray sometimes, right? And again, that's why we're getting two answers. In general, you're pretty safe, right, with picking the positive answer. Because we're insisting right now that down is negative and up is positive and all that kind of stuff, we're living in a zone of safety. But we're going to go into the future to make part of our life easier. We're going to play a little bit dangerous with what directions we're calling positive and negative. Can I take this hat off now? It's a little bit hot. All right. Now I just have wild physics. Okay, let's see. But we can check it, can't we? We can find out which of these answers is the correct one because we've got another way to do it. use the third equation. Vy squared is equal to v naught y squared plus 2a delta y, which is going to be 30.6 squared plus 2 times a negative 9.8 times a negative 75, and I'm going to take a square root to get my Vy. I'm doing the math really fast now because math is boring and I don't want to do it. I got, can't even read my own writing. I got negative 49. Why did I pick the negative answer? Yeah, I can't even write a 9. 49 meters per second. I get I get plus or minus 49, don't I? Because it's a square root. But I pick the negative one because it's going down. And now that I have that, I use the first equation, Vy equals V naught y plus AT. Negative 49 equals 30.6 minus 9.8 times t. Solve that for t and get, once again, can't read my, 8.12. So now I know which one to pick from the quadratic, don't I? Right? So, I'm pretty certain, right, that my time is correct, and that's what they asked me for part B. I've got 2 boxes around it, I better put a unit on both of them. Okay, how do I find the horizontal distance from the launch site? What are they asking me to solve for now? It's delta x, isn't it? So in green here, solving for C, going for delta x, knowing that my time is now 8.12 seconds. How am I going to find, what's my plan for finding delta x? There's only one, right? There's only one tool in the horizontal. So I'm gonna use delta x equals v naught x times t. I've got all that stuff. I've got 25.7 times 8.12, which gets me 200 and we'll call it 9 meters. Checking that's a little bit more difficult, but I'm pretty certain since we got the time right that that's going to be good. And then, I know I haven't done part A yet. Part D, the components of the velocity at impact. So, is that initial or final? That's final, at impact, right? And it's asking for the components. And so what are the components? The Vy and Vx. But we don't have a Vx, do we? We have a V naught x. But what do we know about the horizontal direction? The acceleration is 0, right? Which means we end up with what we start with in terms of velocities. So whatever the initial velocity is, that's the final x velocity. So I know for part D in black here, okay, that V naught x and Vx are the same, which is 25.7 meters per second. And what's Vy? What's the speed it has when it hits the ground? Or right before it hits the water? Negative 49. I already found it, right? Look at that. Checking my work actually made it so that I didn't have to do that part of the problem because I already did it. Okay, back to part A. Part A is a little bit different because if we're doing stuff to max height, what are we going to change?
The V to 0 or Y to 0?
We put something to 0. What do we put to 0? Where's A? A is right. This is going to be part A. No, that's not what I wanted. Part A. We are going to set Vy equal to 0. And again, as soon as we do that, as soon as we tell the final velocity is 0, we are artificially capping this problem. We're telling the tools, start where you start, but end at max height. So now we can go through and find a time. I'm not going to do this because you actually did this yesterday on that practice problem. Okay. But just, I want to call out, if you set Vy equals 0, you've just told it, go to max height. If you set an initial velocity in the y direction as 0, where is this object starting? At max height. In other words, it's been dropped, right? Because a dropped object, right? Or even one thrown horizontally, starts at its maximum height, which we will get to after we do a quiz. Quiz sheets out. What I'd like you to do, okay, for the next 4 minutes, I want you with your neighbors to set this problem up, okay? I want you to make the list, right? Make the list, Vy, V naught y, A, T, delta y, delta x, all that stuff, right? See if you can figure out the initial components of the motion, right? And start setting this problem up with each other. Go.
How should we be grading our quizzes?
Yes, you grade yourself.
Like,
If you missed it, 0. But yeah, show each other, talk it through while you're doing it right now. It's not very loud out there. Are you trapped in a paralysis of thought? Still trying to absorb the question? If you're paralyzed, not sure what to do next, turn to that person next to you, give them your best puppy dog eyes and ask for help.
But I'm confused.
Who's stuck on getting stuff down in this list? Where are you, okay, so where's the stuck? Where's the trouble? What are you wondering? What are your questions? Mitzi?
I don't know, like the one that's next to it, I can't find it.
Okay, the delta x right there. I know it looks like a delta y. That's my x, right? So yeah, question, right? Like what is this? Like what is delta x? It's a horizontal displacement. How do you know it's horizontal? X, right? How do you know it's displacement? Delta, right? So Fritzy's question is valid. Not only just what is it, but like, is there? Have we given any information about how far horizontally this thing goes? We are. There's two numbers up there, right? Okay, doesn't seem like there's a whole lot of information to go on, right? Okay, but 7.7 meters per second. What is that? It's a velocity. It's a speed, right? How do you know it's a speed? It's the unit that tells you, right? Okay. Okay. So and it tells you a speed of, right? Okay. So the delta x is not 7.7, and 0.45 seconds. What's that going to be? Time, right? So even at the risk of making a mistake, okay, go ahead and just start getting stuff down that like is either obvious to you. It could be wrong, but that's okay. Get it down. Don't be sitting there like second guessing yourself, okay? And you're like, oh, is that right? Is that right? Get it down. I say it over and over again. Strong and wrong, right? Commit. Do something. It's okay to be wrong. Let's learn from those mistakes. Okay. So to answer Fritzy's question, do we know what delta x is? We have no idea. Okay. Where does the 7.7 meters per second go?
Starting x velocity,
Starting x velocity? Why do you say x velocity?
because that's for the horizontal motion.
It's launched which way? Horizontally. What does that mean about its vertical speed? Has to be 0. If something is launched vertically, what do you know about its horizontal speed? 0. If it's launched horizontally, what do you know about its vertical speed? 0. Right? Horizontal and vertical mean only x or y. So, I don't know how fast it's going when it hits the ground. They don't tell me any of that information, and I can't assume. But I do know that its vertical speed is 0. All right, what do we know about its acceleration? It's a projectile, so it's going to be in free fall, so it's negative 9.8. Do we know how high above the ground it is? No. Do we know how far it falls? Nope, don't give me any of that information, right? And do I know what my V naught x is? Sure do. 7.7. You know, like saying you're going, Mr. Balogh, we didn't get any of that. We're doomed. No. Now you know, right? And knowing is how you know stuff. Just think about that for a little bit, okay? You learn by practicing, by being exposed to these things. So now when you're going through your homework and you see the word horizontal or it's launched horizontally, you can refer back to your notes and know what? Know that V naught y is 0. That V naught x is whatever number they, right? Okay, I'm exposing you to these different kinds of problems you might come up against, right? To help you learn. So don't get down on yourself thinking, oh my gosh, there's no way. No. You're doing great. You're actually, if you're confused right now, you're perfect. Okay? We want to get as much of the confusion out of the way before the exam happens, right? Okay. So, this is what I've got. I'm still not sure it's actually right. What do they want to know? How high above the ground? What are we solving for? We're solving for delta y. This is what we're after. Those are the things we know. What are we going to use? Second one? So the second one, we want that. We know that, don't we? And we know the time. And we know, right? Second one, delta y equals v naught yt plus 1/2 ayt squared. So the plan is use second equation. I don't even have to do math here, right? I mean, like some arithmetic, but I don't have to do any algebra, right? There's no quadratics to speak of because it's already solved for me. It's 0 times 0.45 plus 1/2 times negative 9.8 times 0.45 squared, which gets me negative 0.99 meters, or I'd say negative 1 meter. What's the negative sign mean? It means it went down. Is that what it does? If you launch something horizontally, is it going to fall? Yes. Okay. The question did say, how high above the ground was the ball thrown? So if I went to Wiley Plus and put in -1, it would probably say wrong red box, right? And I'd be like, well, no way, I did it right. How high above the ground would be a positive answer, right? So sometimes you got to argue with Wiley Plus too, right? But always try the opposite of whatever answer you put in first, right? See if it wants the other way around. Okay, so we got that. We know as well. Okay, what was the ball's speed? What is the ball speed when it strikes the ground? Okay, this is a bit of a loaded question. What is the ball's speed? What are they asking for? It says speed. How are speed and velocity different from each other? One has a, not distance, a direction, right, associated with it. They're just asking for how fast it's going. So, which of the things in this list is the speed that it has when it strikes the ground? It's not V naught something, because V naught means what? It means initial. It's not Vy. It's not Vx. It's a combination of Vx and Vy. Because what are Vx and Vy? They're the components. They're the horizontal and vertical pieces. And did the question say what is the vertical component of its speed when it hits the ground? No. Did it ask for what is the horizontal velocity when it hits the ground? No. It asked for how fast is it going when it hit the ground? That's not Vy, and it's not Vx. It's the vector sum of those two things. Why?
Because if it's V and X, like, I don't understand.
Yeah, Kamari said I'm scared, and she's not wrong. Okay, so there's the object flying through the air, right? The path that it takes. When it gets to this point right here, the toolbox can tell us Vy and Vx. What's Vx going to be, by the way? Not 0. 7.7. It doesn't change, right? So Vx is equal to V naught x is equal to 7.7, right? So we know that one already, okay? But the ball is moving horizontally and vertically. It's two pieces of the motion. What they want is how fast does it hit? That would be the length of this vector right there. The sum of those two components put together. And that's the one that we need to find. So how are we going to find it? We're going to find Vy first. We know Vx, we need Vy. So how are we going to find Vy? First equation? Right? So it starts with 0 minus 9.8 times 0.45 seconds. That got me negative 4.41 meters per second. So this is equal to negative 4.41 meters. So now I have a triangle. I have a triangle that's 4.41, and it goes over 7.7. So it looks something like that, right? Okay. If I have the x and y pieces, if I have the two legs of a right triangle, and I want to find the hypotenuse, what do? Pythagorean theorem. When you have the components, you can use the Pythagorean theorem to find the magnitude. 7.7 squared plus 4.41 squared. I don't put the negative sign in because it's squared, everything happens anyway. And this is 8.87 meters per second. So, what do you learn from this? If the question asks you for how fast is it going when it hits, you're not answering just Vy or just Vx. What are you doing? You're putting those vector components back together. We have to break the problem up into horizontal and vertical components to do the problem. Because the toolbox only works in the vertical and then the horizontal. The only thing that's the same between these two is time, by the way, right? But everything else, we got to break it up into two pieces. The reason we have to break it up into two pieces is because gravity acts which way? Down, in the vertical direction. But we're combining horizontal and vertical motion. So the power of vectors allows us to break those two things up. And then oftentimes we're asked to recombine them at the end. Find out how fast something is when it strikes the ground. Or maybe sometimes, so this brings up a good point here. Sometimes you are asked to do variations on a theme. In music theory, variations on a theme is like if you take Row, Row, Row Your Boat and like play it jazzy, okay, versus maybe rock and roll style and all that kind of stuff. The theme is the same. It's still Row, Row, Row Your Boat, but the way it's played is different. In physics, this takes the form sometimes of problems where, say, let's say somebody's shooting a basket, okay? So we've got court, we've got the basketball rim, right? We've got the players, right? And we know how far away horizontally the rim is. We know how high above the ground the rim is. And we know that the player throws the ball at like an angle of 40 degrees. But we don't know how fast the ball is thrown. We know delta y, we know delta x, we know that the vertical acceleration is negative 9.8. But here, we're being asked to solve for the initial speed of the ball. Like how fast does the player have to throw it? You're going to conquer a problem like this the same way we've conquered all the other problems. Where do you start?
Visualize.
You visualize. You make that list, right? And that list comes directly out of the toolbox. T, delta y, delta x, v naught x, right? But we don't know what v naught x and v naught y are. We know that we know their angle, but we don't know what their speeds are. We know the acceleration is negative 9.8. Hopefully they give us a time of some kind, okay? We're given a delta y, we're given a delta x. We'll probably give you a time, okay? The problems might do something like the ball reaches maximum height just as it enters the net. But what do you know about the vertical speed at maximum height? It's 0, right? Okay, so you can work backwards to find out what the initial y velocity is. Once you have that, okay, we know that v naught y has to be equal to v naught sine, in this case 40 degrees, and then we can find the speed that it gets launched at. So what I'm trying to communicate here is that on your homework you've got a variety of problems. They are all approached exactly the same way. You visualize, you come up with a plan in your strategy, and then you do it. When that doesn't work, you go back, you check things, right? Okay, remember, assume one of the pluses wrong first, okay? And then keep working that, changing your visualization, updating as new information occurs to you, and ideally working with somebody else to make that process as fast as possible. Catching each other's mistakes, bouncing ideas off of each other, and so on and so forth. Okay, so This Saturday, you have chapter 2 and part 2 of chapter 1 due. And then next Wednesday, chapter 3. We have grasp on Friday for chapter 2 and the second half of chapter 1, right? You can come in for chapter 3 if you're already there. On Tuesday of next week, we can review and we'll have an opportunity to go over chapter 3 homework. Try to have chapter 3 homework attempted by next Tuesday. Alright? So we can button up and close things up so that we can be ready for our exam on Thursday. Chapter 3 is due next Wednesday. Have a fantastic rest of the day!